In this module, we explore the capacity of bending members, and bending members are the most common type of timber elements that structural engineers have to design. We'll look at the bending elements, limit state design, we'll look at design capacity equation, the capacity factor, all of the modification factors, the K factors, the characteristic strength, and a worked example at the end. Now, bending members are found nearly everywhere, in roofs, in walls, in floors. Primarily anything with the word joist in it is going to be a bending member. Beams are bending members, bearers are bending members as well, rafters, purlins, they're all functioning as bending members. Lintels over openings function as bending members. Studs, vertical members in walls, function as bending members under lateral loads. Typically wind loads are going to cause a stud to become a bending member. And there are many other types of bending members as well. So all of these pictures are featuring bending members. Typically, bending members have to be checked for the strength limit state. There is no question about it. Every single bending member has to be checked for the strength limit state, and often if there are deflection limits, they're also going to be checked for the serviceability limit state. If we're looking at long span bending members, we're not going to be able to use rectangular sawn timber. We're going to have to use an engineered wood product, something like glulam or LVL, to span very long members. And often, bending members will also have some compression and tension forces that they have to resist under some load combinations. So they may have to resist combined actions, but they are going to have to establish their bending capacity in order to check their combined actions. Now, limit states. Essentially, when we're thinking about limit states, there are two that we often think about. The serviceability limit state we've already explored, and it is how does the member perform under regular loads? Does it deflect too much? So in this case here I'm applying small loads and it's deflecting a little bit. Is the deflection too much? The serviceability limit state is what addresses that question. However, the strength limit state is different. Under extreme loads, we want to be sure that the member doesn't break like that. So that has exceeded the strength limit state. The consequences of having a beam break like that could be fairly catastrophic. It could lead to injury of people or loss of life. So exceeding the strength limit state is something very serious. As a result of that, all members have to be checked for the strength limit state. And often we find that with bending members, if they're shorter members or carrying very high loads, that's when the strength limit state is going to be really important. There are three different failure modes that we have to be concerned about for bending members. And these three failure modes each have their own design capacity, and that is shown on this slide. So the top one is the bending capacity. And that's the capacity that we've already discovered. That's a capacity limited by a flexural fracture of the timber. The next one is the shear force. So a shear failure looks quite different to a flexural failure, and you can see a picture there of a piece of timber that has a shear failure in it. And finally, there is the bearing failure. Bearing failure is going to be crushing of the timber member over the top of a bearing or underneath a point load. So in those cases, exceeding the bearing capacity is going to lead to local crushing of the timber fibres. All three of those equations have a commonality. There's a capacity factor, some modification factors, and at the right-hand end of the equation is the notional capacity of the timber element. The design equation. In the design equation, we're looking at making sure that the factored moment from the strength limit state loads is smaller than the design capacity of the member. So we evaluate all of the strength limit state loads, find the bending moment that those loads cause in the member, and make sure that our design capacity is larger than that value. So the design capacity is given by this expression for a bending member. And you can see the capacity factor, you can see all of the modification factors that account for the environmental conditions that the member is going to be found in. Now, all of those factors look a little bit complex, but They all model the behaviour of the timber, the understanding that we have of the behaviour of a bending member in service. At the far right hand end is F prime B, the bending strength of the timber, times its section modulus. And that gives the notional capacity of the member, which when modified by all the modification factors, cause us to find its design capacity. The first of those factors is the capacity factor. The capacity factor leads to a consistent level of reliability across all building materials. So all structural materials have their own capacity factor, and the timber capacity factors are designed to give exactly the same reliability as steel members and concrete members. It's a function of the product. It's a function of the building in which that product is going to be used and the type of element it is going to be used in. So the capacity factor table looks like this. In the left-hand column, you can see the different timber products. As we go down the column of timber products, at the bottom we have the ones with the tightest control over their design properties. And so with a tight degree of control over the design properties, there's a high level of inherent reliability in those anyway. As we look across, we see different categories in which the timber might be used. Category 1, Category 2 and Category 3, and we're going to explore those over the coming slides. The first decision we have to make is it a primary member or a secondary member? And essentially what we're looking at is the structural form in which the member is going to be used. If we're using the timber member in a system where there are a large number of parallel members that are all working close together, then the failure of one member may not cause a complete structural collapse in that the others can pick up some extra load. We call that a secondary member. On the other hand, if the member is working entirely on its own and doesn't have others that it can shed load to if it starts to fail, that is definitely a primary member. So primary members function in isolation. Secondary members have the capacity to share the load between each other in the event of a failure. The consequence of failure is what we're thinking about. If the consequence of failure of an individual member is to cause a collapse of part of the structure, that is a primary member. If, on the other hand, the structural form can bridge over a failed member, then that is likely to be a secondary member. So in viewing a structure, we have to think carefully about what is the consequence of each member failing. In the left-hand picture, we're looking at a large industrial building with a lot of portal frames. Each portal frame has a whole bunch of purlins sitting over the top of it. Each one of those purlins has got purlins immediately adjacent to it, so a failure of a single purlin may not necessarily cause a failure of the whole structure. However, the portal frames themselves, if one portal frame fails, the purlins aren't able to span over the 16 metres that they now have to carry load from in the event of failure of one portal frame, and as a result of that, we say that that portal frame is a primary member. If we think about the purlins themselves, and in the right-hand picture the trusses, there are lots of closely spaced trusses, each of which don't carry a huge amount of load on their own. So they are secondary members as well. So primary members, larger members without the ability to share, secondary members, smaller members with the ability to share load to others. Finally, structure type. Wind loads, earthquake loads and snow loads are all a function of the building importance. The higher the level of importance of the building, the more load we have to design for. And that higher importance level is going to lead to loads with higher return periods. Lower capacity factors are used in conjunction with those high load levels to give an appropriate level of reliability for the structure. So, in summary on capacity factors, first step, and that's the red rectangle on this slide, is to look at the product, work out which product we're using, and that will tell us which row we're looking along. The second thing is to work out the application category of the structure. So we're making a decision, is it a primary element or a secondary element? If it's a secondary element, we're looking in category 1, which is the green shaded rectangle on this slide. If it's a primary element, we have to ask one more question, and that is, what type of structure is it in? If it's in a structure with a post-disaster function, then it's got a higher level of importance, and we use the category 3 factors on the very right-hand side of the table.